So this will be the last video that I'll make right now for chapter 1. A couple of comments before we get started here. There is a little bit about kinetics, the mathematics, quantitative kinetics, so rate laws, the Arrhenius equation, and most of that content on the whiteboard up there is contained in box 1-1 and box 1-2. And there are sections in your OpenStax textbook that I referenced. I don't have them off the top of my head. I think it's like 12.1 to 12.6. Now, we're not going to do a lot with that in this chapter as my original game plan. If we get interested in that, that's fine. I can cycle back and make additional videos, but it's really a question of time and coverage so that we really spend more time getting the big picture from these chapters. And if we spend a lot of time on kinetics, that's going to be a lot of computations and a lot of time. I put a couple of homework problems based on boxes 1.1 and 1.2. And we'll see how we do. If I need to make another video, I will. But I'm going to make a few references to some concepts from kinetics today, but not too many. Also, you'll want your book today, specifically for figure 1-1 or 1-1 on page 4. I had a slide with this on it. It basically just shows the concentration of ozone in the troposphere, which is not very much, and then in the stratosphere, which is much, much higher because it needs to be there. So just, you can either have that handy or just take a look at it, because I'm just going to reference that one. And let's get started. Also, occasionally I like to throw out current events. So today's date is, what is today's date? May 24th. And there's actually an interesting current event going on, potentially catastrophic, going on in California. There's a giant tank of a chemical called methyl methacrylate. I think it's something like 15,000 gallons of this. And there's a valve on the tank that is malfunctioning. And they're worried that the tank might explode. And actually, a best case scenario, if they can just get the tank to leak, then they can contain the liquid. But it's a potentially dangerous situation that we could always use as a case study in this course. Now, that wouldn't be anything to do with the atmospheric chemistry directly, but it's always interesting to talk about current events in environmental chemistry, which unfortunately usually translate into environmental disasters. So occasionally I throw current events on there. All right, let's get started. There's only 2 slides left and a lot of text that I want to add. So here are the slides, and there's a very famous graph called the hockey stick graph. You can look that up. That was put together by a climatologist named Michael Mann. I believe he's at Penn State University at the moment. When he did this graph, I think he was at the University of Virginia. Interesting story, you can look it up on your own. There was some political pressure that was put on him because he was a big advocate for climate change, and he ended up leaving the University of Virginia and going to Penn State. So he's written quite a bit about that if you want to read a little bit about Michael Mann and the famous hockey stick graph, which I'm just going to make a couple of references to here. I just put that there because it's a graphic that relates to what we're doing. Okay, probably a little bit too much of an intro there. And so let's come out and finish this off. And these slides, these notes don't necessarily have much to do with each other, so hopefully this won't be too long, but I think it's time to finish off the first chapter. Okay, also wearing a shirt from my alma mater, the University of Delaware, so I'm not being disloyal to Shippensburg. And I think I realize the color blue does not appear very well on this chalkboard, so I'm going to just stick with the black and probably just write the headings as I go just to keep myself organized. So you can use the exact headings that are on the slides if you want to. I'm just making these short. So, intro to concentration units. And as I'm apt to do, I might not exactly just write down everything exactly as I have it down here, but might give a little bit more background. So when we measure things in the atmosphere, it's not the same thing as we measuring things like when you go into a laboratory and prepare a solution. And you prepare a solution, say, so many grams per liter of solution, so many milligrams per liter of solution, so many moles per liter of solution, which is called molarity. The units in atmospheric chemistry are often different than that. Sometimes they are the same, but not very often. So we need a different mindset, if you will, for measuring things in the atmosphere. Because one thing I like to teach in any science class is that you pick the units that make sense for the context that you're dealing with. An example, we measure energy in kilojoules per mole for chemical phenomenon. Now, some disciplines would not use kilojoules per mole, and for wavelength and things like that, we use nanometers. So that's just an example of what we do there. So this is really just an introduction to the concentration units. In fact, I don't even think this is an explicit part of Chapter 1, but it's a way for me to just say, what are the different units that we can expect to see going forward? So on figure 1.1, page 4, I'm not going to try to draw that. I could, it's not that hard. You'll notice there that the units are molecules per cubic centimeter. You might recall from chemistry classes before, a cubic centimeter is the same volume as a milliliter, but since we're not dealing, milliliters tend to be used for liquids, so we're dealing with the atmosphere, so the gaseous state. So we don't use milliliters, but cubic centimeters. And molecules, it's a kind of an interesting way to do this. And just to give you an idea, on figure 1.1, if you look at the maximum concentration of ozone in the stratosphere, you can get an estimate of that just by looking at the graph. So if you want to look at the graph and just get your own estimate, what I came up with from that figure was the maximum concentration of ozone that you're going to see in the stratosphere is approximately 4.6 times 10 to the 12th. You'd expect that to be a large number. Molecules of ozone per cubic centimeter. So that's really all I'm saying about this now. And some of the kinetics problems that are done in these two boxes use those units, just to get used to seeing those. Another unit that we often use is partial pressure. Now this is something that was a topic that you're asked to review from gases and ideal gases. It's really not that difficult of a concept. It's especially not a difficult concept when it comes to the atmosphere for reasons I'm going to kind of explain. So the general rule here is if you have a mixture of gases, the total pressure is equal to the sum, from statistics, the sum of the individual pressures of the gas. So you could write here, a lot of books describe this as P1 plus P2 plus P3 dot dot dot, but I think you're sophisticated enough to handle the statistical notion. So you add up the partial pressures of the gases, and that equals the total pressure. Now in atmospheric chemistry, that total pressure is often just the atmospheric pressure. So on the ground level, you just go read a barometer. Or as you go higher and higher and higher, you're going to get less atmospheric pressure, precisely for the reason that there is less atmosphere. So the barometric pressure in Denver, Colorado is going to be, on average, much less than the atmospheric pressure in Carlisle, Pennsylvania, where I'm currently standing. So that's what we're talking about here. And you might remember some units. Pressure can be measured in whatever units make sense for the scientific field that you're in. Engineers will still use pounds per square inch, PSI, often. And units that we will deal with are atmospheres, millimeters of mercury, kilopascals, and occasionally, I don't see this one very often, bar. Oh, by the way, mmHg is the same thing as torr. So I'm not going to go through these. There are unit conversions for each of these. How many millimeters of mercury is an atmosphere? 760. So those are some things. How many kilopascals is an atmosphere? I'm doing this from memory. I think it's 101.325. You can fact check me on that. Kilopascals is an atmosphere. So be able to shift between the units. I think the book primarily sticks with atmospheres, and that's fine. That's fine. And What's nice, one thing that's really nice, is under the conditions that we deal with atmospheric chemistry, we're dealing with pretty reasonable temperatures and pressures. They're not extreme, so we can make the assumption of an ideal gas. If you don't remember what an ideal gas is, go back and look that up. But basically, an ideal gas is you assume that molecules are all the same, that these little point masses just bouncing off of each other and bouncing off of the container that they're in. That's what an ideal gas is. You assume that they're not interacting with each other and they don't take up any space. That's what a point mass means. And when we make that assumption, an equation is very useful called the ideal gas equation. If you've had chemistry at all, ever, you've seen this equation. And just a couple of things about this. There are some homework problems with this. When you use this equation, let's see, so P is pressure, V is volume, N is the number of moles. So we have to remember a little bit about moles. R is a constant called the universal gas constant, and T is temperature, but we have to use the Kelvin temperature scale. So please remember that when you take something in degrees Celsius, you add 273.15 to it, and that converts it to Kelvin. Okay. Again, I'm not going to review that temperature scale. If you need to review that, please go review that on your own. And the value for the universal gas constant comes in two flavors, if you will, with two different sets of units. 0.08206 liters times atmospheres over Kelvin times moles. Now that leads you to a couple of things. That means that when you use this equation with this constant, the volume must be in the units of liters, and the pressure must be in units of atmospheres. Moles are moles, and assuming you understand temperature, that's in Kelvin. Another value for R, which I think we use from time to time, is the one that uses the more systematic base units from the SI system, from the International System of Units. 8.31451 joules per Kelvin mole. Now, we don't have time to do all the derivation here, but if you liters and atmospheres, when you reduce those down to their base units and do all the cancellation, you end up getting joules. It's kind of an interesting derivation to do. But these are two versions of this constant, depending on the application that you're doing. Okay, now I want to try to fit this all on one board because I have to erase it. The other unit that comes up that's very common, and you can look at the hockey stick graph for this one, I think. Let me take a look. Yeah, if you look at the hockey stick graph, the x-axis is the year, from the year 1000 up to the year 2000. That's pretty amazing. So the x-axis covers 1,000 years. You'll probably never see a graph that covers that unless you study archaeology or something like that. And the y-axis on the left side is ppm CO2, and then the right side is temperature. So because that's what we're concerned about with climate change, is how much does the temperature go up as the carbon dioxide goes. The point of this graph is to show that the temperature of the Earth, the average surface temperature, I think is what that is almost perfectly correlated with the carbon dioxide. That's what the hockey graph is indicating. Okay, but the point for this part of the lecture, I guess I'll fit it in over here. So, sorry, a little sloppy. Is another unit of concentration called molecular fractions. What does that mean? Well, that means literally what it means. And there's different ways to do this. Parts per, and then fill in the blank. Parts per million, parts per billion, parts per trillion. And what does that mean? So parts per million ppm, and million in scientific notation is 10 to the 6th. Parts per billion is 10 to the 9th. Parts per trillion not thousand, ppt, I guess could be parts, confused as parts per thousand, is 10 to the 12th. So what does this mean? As an example that I have for you here is on the graph, on the hockey stick graph, in the year I'll just use this as an example. In the year 1900, if you find not the temperature side, but the ppm side. So, sorry, this is a really sloppy lecture. This is just underneath number 3. So, in 1900, you have CO2 levels that are approximately, this is just how I read the graph, 295 ppm. Now what does that mean? Well, that literally means 295 molecules of CO2 per 10 to the 6th molecules of everything, which we're just going to call air. That's literally what it means, is how many molecules are present in a total collective of 1,000,000 molecules of air. So it's a unit of concentration, but it's a little bit different mentality than something like molarity. Now, when I taught this course for the first time, that was a complete mind shift for me. I don't know what science background you're coming from, but if you have some experience with atmospheric chemistry, that's going to make sense to you. Now, I think I was going to make this the last video. I'm going to make a call an audible here and make this the second to last video, because units of concentration it's a reasonably good standalone question. And I'm going to add something here, which I was thinking about, but I think I'm going to do it here. Another thing about an ideal gas, so that's an example, let's call that example 1. Okay, example 2. Let's assume you go to a barometer somewhere and you measure the atmospheric pressure is 0.993 atmospheres. So almost 1 atmosphere. So in Cumberland County, where I'm standing, we're about 500 feet above sea level. So standard 1 atmosphere assumes perfectly at sea level. So that's a reasonable one. The partial pressure of oxygen gas is approximately now, I don't have my calculator out, so sorry, you can do the math. Now, why did I do that? You might recall from one of the previous lectures that air is approximately 20% oxygen. Great, that's a useful piece of information. So what that allows us to do is that if you know the total pressure and you know the percentage of a component of gas in that mixture, you can calculate the partial pressure of that component. Nitrogen would be about, what's the percentage I gave you? 78%, so 0.78 times that. And the point is this, is that you can correlate what we know about the composition of the atmosphere to how much pressure it contributes. And that's all comes back to concentration as well. So that's just an introduction. How do we measure things in the atmosphere? Practically speaking, usually the things that I read about like when you read about the atmosphere in media sources, usually you're seeing these ones. Parts per million, parts per billion, parts per trillion. So things that exist in part per million, that's pretty high concentration. If something in the atmosphere, say a pollutant, exists in a part per trillion level, we tend not to be as concerned about it. But these are the ways we measure it, especially when it comes to things like health effects and more environmental impacts or ecological impacts. Okay, so I just kind of added that there at the end, and let's stop this. And the last video we're going to do is the last section of the book, but I don't want to get ahead of myself. I'll give you a preview of that one coming up.